17 meters. That is wider than a 4-lane highway, and it is the diameter of the cutterhead on the largest tunnel boring machine ever deployed in the United States. The machine weighed approximately 7,000 tons. It stretched 99 meters long, longer than a Manhattan city block. It cost $80 million. And to place it where it needed to go, engineers dug a launch pit 60 feet deep into the Seattle waterfront, lowered the machine in pieces, and assembled it underground. No road, no bridge, and no crane on Earth could have carried it whole. The machine's name was Bertha. Her job was to bore a 2-mile tunnel 30 feet beneath a working 6-lane highway, while that highway stayed open for traffic above. She would advance by pressing a rotating steel disc against the rock face, with a total hydraulic thrust of 72,000 tons, moving forward roughly 2 meters every hour, placing a completed ring of concrete behind her with every advance. That is not how most people picture a tunnel getting built. Most people imagine drills, controlled explosions, or an industrial army of workers chipping through rock in shifts. Not a 7,000-ton machine that cracks rock through compression and installs its own tunnel walls in real time. The reality is more precise than any of those images suggest, and when something goes wrong with it, it can take years to fix while the city above carries on without knowing. To understand why that happens, and what makes these machines work at all, you have to start with the thing on the front. The most important thing about a TBM cutterhead is that it does not drill. Drilling implies a bit cutting material away. The disc cutters on a TBM do something different. They roll across the rock face under intense compressive load and weight. The rock fractures on its own. Each disc cutter is a hardened steel ring, typically 17 to 19 inches in diameter, mounted on a bearing that lets it rotate freely as the entire cutterhead turns. The machine's hydraulic rams push the head into the face, loading each disc with roughly 250 to 300 kilonewtons of force. For reference, that is approximately the weight of a fully loaded cement mixer pressing through each individual ring. When that load bears on rock, the material beneath the disc cracks outward. On a rotating cutterhead, dozens of discs pass over the same patch of rock in slightly different arcs with each revolution. The cracks from adjacent passes intersect, and chips of rock fall free. On Bertha, 864 cutting tools covered a face 17 meters across. The cutterhead turned at about 1.2 revolutions per minute. The chips fall into an opening at the center of the cutterhead, enter a screw conveyor, and travel back through the length of the machine onto a belt that carries the material to the surface. Engineers call this material muck. A large TBM moves an amount of rock roughly equivalent to an Olympic swimming pool for every 250 meters of advance. Behind the cutterhead, the machine's trailing systems extend another 50 to 80 meters. The segment erector, the grouting system, the ventilation ducting, the electrical supply, the control room. As the cutterhead advances, the outer steel shell of the machine holds the surrounding ground from collapsing. Workers in the tail section install precast concrete segments, curved panels 1.6 meters wide and about 400 millimeters thick, bolted together into rings. Each ring forms one completed meter of the finished tunnel wall. A robotic erector arm picks each segment from a feeder car, rotates it into position, and presses it into place. Workers bolt the adjacent pieces together. As soon as a ring is complete, the hydraulic rams push forward into the next advance and the cycle repeats. Simultaneously, grout is pumped through ports in the tail shield to fill the annular gap between the new concrete and the surrounding ground. Without that grout, the soil above could settle. In a city, 30 millimeters of settlement can crack building foundations and rupture buried utilities. A tunnel boring machine excavates, supports, and lines the tunnel in one continuous operation. There is no moment when bare ground is left unprotected. This is why TBMs took over urban tunneling, and why the alternative, drill and blast construction, is now confined mostly to remote locations where there are no streets, no pipes, and no foundations above. But there is one aspect of TBM operation that rarely gets discussed when people look at photos of the cutterhead. How does the machine know where it is going? GPS does not work underground. Radio signals do not penetrate rock. A TBM drilling through a city navigates in complete electromagnetic silence, and it must arrive at its destination shaft, which may be 2 or 3 miles away, within a positional tolerance of 25 millimeters. The thickness of a finger. The solution is a laser total station, a surveying instrument mounted in the completed tunnel behind the machine, firing a precisely aimed beam at a prism fixed to the TBM itself. The instrument knows its own location. It measures the angle and distance to the prism continuously and calculates the machine's exact position in 3 dimensions. The operator sees this data in the control cab in real time and adjusts the hydraulic thrust accordingly, pressing harder on one side to steer, tilting the angle of advance to correct vertical drift. The system updates fast enough to catch a deviation before it compounds into something unfixable. In practice, TBMs drift. A small error in the first 100 meters can become a significant problem over a kilometer if it goes uncorrected. Overcorrection creates the opposite problem. The navigation record of a TBM, plotted from launch to breakthrough, looks like a slightly wavy line, the accumulated trace of corrections and counter-corrections spread over miles of rock. Engineers who review that record can reconstruct every steering event in the machine's history, deviation by deviation, like reading the flight data recorder of an aircraft that never left the ground. While the machine navigates and the rings go in, a crew of 15 to 20 people works inside it around the clock in rotating shifts. The environment near the cutterhead routinely reaches 45 degrees Celsius from machine heat and geothermal temperature. Noise at the main bearing requires continuous hearing protection. The tunnel is narrow, wet, and perpetually filled with the smell of pulverized rock and hydraulic fluid. In soft ground or below the water table, the stakes are considerably higher. If the pressure at the face is not controlled, soil and groundwater rush into the machine. To prevent this, TBMs operating in soft urban ground use one of 2 approaches. Either a pressurized bentonite slurry fills the chamber behind the cutterhead to hold the face back, or an earth pressure balance system regulates the rate at which muck leaves through the screw conveyor. Both require the face to be maintained at a pressure above the ambient groundwater. When workers need to enter that pressurized chamber to replace worn disc cutters, they follow protocols borrowed from saturation diving: pressure equalization in an airlock, limited time in the compressed environment, controlled decompression in a designated chamber afterward. Decompression sickness is a documented occupational hazard in compressed air tunneling. The condition has killed workers in this industry at every stage of its history. Disc cutter replacement is not quick. Each cutter weighs 100 to 150 kilograms. Replacing a full set on a large machine requires multiple interventions over several days. Every hour of that work accumulates cost against a machine that runs at roughly $100,000 per day in fixed operating expenses, regardless of whether the cutterhead is turning. The crews who do this work are specialists. A TBM operator on a major project in the United States or Western Europe earns between $80,000 and $130,000 a year. The machine minders and segment erector operators earn comparable wages. Compressed air workers who enter the pressurized face chamber receive hazard pay on top of their base rate. A full drive on a project like Bertha's takes months to years. The workers commute underground. They walk or ride a man car into the tunnel at the start of a 10-hour shift and do not see natural light until they come out. In the later stages of a long drive, the walk from the portal to the active face can itself take 20 minutes. Lunch is eaten in a break room carved out of the tunnel, under fluorescent lights, with the machine idling behind a wall of sound insulation about 40 meters away. That economic pressure explains a great deal about what happened in Seattle. The concept of a tunneling shield was invented by Marc Isambard Brunel in 1818, developed to solve the specific problem of digging beneath the River Thames without immediate flooding. His rectangular iron frame protected the excavation face, while workers dug in small sections inside it. The Thames Tunnel, completed in 1843 after 18 years and 8 deaths, was the first tunnel successfully bored under a major navigable river. James Greathead refined the shield into a circular form in 1869 for the Tower Subway, also under the Thames, and added the practice of immediately lining the bore with cast iron segments placed ring by ring. That pairing, circular shield, with an immediately installed tunnel lining, is structurally identical to what a modern TBM does. What changed over the following 150 years was scale, drive power, and navigational precision. The operating logic is the same. In December 2013, after advancing roughly 300 meters of her planned 2-mile drive, Bertha struck a steel pipe casing in the ground. It was a monitoring well installed during a 1990s environmental survey. It was not on the utility drawings the engineers had been given. The impact damaged the seals on the main bearing. The main bearing is the central rotating component connecting the cutter head to the drive motors. When its seals fail, soil and water enter the housing and destroy it from inside. Bertha stopped in February 2014. She had completed about 10% of her tunnel. The repair required a rescue shaft dug directly above the stopped machine, 120 feet into the ground, to give workers access to the bearing. Digging that shaft alone took months. Replacing the seals, rebuilding the bearing housing, and recommissioning the machine took close to 2 years. Project cost overruns ultimately exceeded $200 million, on top of the original contract. The highway directly above, State Route 99 on the old Alaskan Way Viaduct, remained open throughout every month of that period. Bertha resumed drilling in December 2015 and broke through at her destination shaft in April 2017. The tunnel opened to traffic in January 2019. The viaduct it replaced, a double-deck elevated road built in 1953, was then demolished. A structure that defined Seattle's waterfront for over 60 years was removed because one machine drove a hole through the city's bedrock and replaced it from underneath. Bertha's breakdown is not unique in kind. TBMs fail more often than the public notices, because when they stop under a city, the repairs happen underground, and the surface disruption is often managed without any visible shutdown above. The machine is the most efficient tool for boring in an urban environment, and, when it stops moving, among the most expensive things in construction to fix. It cannot reverse. It is engineered to move in one direction. Once launched, the economics of the entire project depend on it completing the drive. This is why contracts for underground construction have become some of the most disputed documents in the engineering world. The question of who bears the cost when the ground turns out to be different from what the surveys predicted is negotiated for months before any machine moves. Unexpected geology, an unmarked pipe, a harder rock layer than the model showed, an aquifer the borings missed. Each of these can become a 2-year halt and a 9-figure overrun. The cities currently building the most ambitious TBM programs have absorbed those lessons at cost. The Grand Paris Express, a 200-kilometer expansion of the Paris Metro, has used multiple TBMs simultaneously beneath the city at various stages of construction. London's Crossrail project used 8 machines, each named after a woman with a connection to the city's history. The Gotthard Base Tunnel in Switzerland, the world's longest railway tunnel at 57 kilometers through the Alps, required 17 years of construction and multiple machines working from several access points simultaneously. The cost of tunneling in dense urban geology typically runs from $150 million to $500 million per kilometer, depending on soil conditions, tunnel diameter, and the density of existing infrastructure above. The machines themselves are custom-built for each project's geology, and often left in the reception shaft at the end of the drive, because disassembling and removing them would cost more than abandoning them. The disc cutter surfaces on modern machines are coated in tungsten carbide to extend service life. Navigation systems can model the machine's positional drift in 3 dimensions, and project its location 24 hours ahead based on current steering inputs. Some TBMs now carry ground-penetrating radar systems that probe ahead of the face to detect voids or obstructions before the cutter head reaches them, buying the crew time to adjust rather than react. What none of these systems fully resolves is the foundational constraint of underground construction. The ground is never completely known. No borehole survey, no seismic profile, and no geotechnical model captures everything that is there. The machine always meets the actual ground, not the modeled ground. The engineers who launch a TBM know this. The contracts governing the project are structured around it. The crews who work inside the machine live with it, shift by shift, for however many months or years the drive requires. When Bertha broke through in 2017, the event was covered as a milestone for Seattle's infrastructure. What it actually represented is harder to define. The completion of something that should not be possible by any ordinary engineering measure, a machine the size of a city block navigating through rock it cannot see, placing a finished tunnel behind it in real time, and arriving within centimeters of where it was aimed after 2 miles of blind advance. But here is something most people who follow these projects never think about. The longest stretches of buried infrastructure on Earth are not tunnels at all. They do not go through rock, they run through water, sometimes through more than 4 miles of it, under the open ocean. There are over 400 submarine cables crossing every basin on Earth, carrying the vast majority of the world's internet traffic between continents. Each one was laid by a single ship, moving at a few kilometers per hour, paying out a line no thicker than a garden hose, over distances that make Bertha's 2-mile drive look like a parking lot maneuver. One ship, 6,000 kilometers of cable. Across the open Atlantic. How a vessel navigates that operation, keeps tension on a line descending to the ocean floor in water 4 miles deep, buries the cable where it touches bottom to protect it from trawlers and anchors, and completes the entire run without a single break in the line, is a problem of logistics and engineering that belongs in the same category as what you just watched. It is in several ways considerably stranger, and the answer is not what you would expect. If you want to understand the full picture of what gets buried to keep the modern world connected, that story is next.